Here I will talk about our paper set by CVPR2023 DSVT, Dynamic Sparse Voxel Transformer with rotate set. In this paper, our DSVT is a transformer architecture designed for sparse data, such as 3D point cloud or 3D voxel. It's a single-thread window-based voxel transformer for outdoor 3D perception, especially for autonomous driving with large-scale perception range. In order to efficiently process sparse points in parallel, we propose dynamic sparse window attention, which partitions a series of local regions in each window according to its sparsity, and then compose the feature of all region in a fully parallel manner. First, let's provide some context. With the development of artificial intelligence, including autonomous driving, virtual augmented reality, robotics, and medical image, there are increased demand for 3D perception. 3D point clouds are widely used in 3D perception. They are suitable for real-time scene understanding and have a simple data format represented as n times 3 matrix. However, processing point clouds presents a challenge due to their sparsity and irregularity. Traditional grid-based operations are not useful to unordered point cloud data. Point clouds are widely used in autonomous driving due to their resilience to lighting, making them valuable for accurate perception in challenging scenarios. Compared to image, point clouds provide sparse and irregular data that require specialized processing techniques. Point cloud has sparse and irregular data format which cannot be processed with existing convolutional neural network directly to support sparse feature learning from raw point clouds. Previous method mainly applied custom sparse operations such as point net plus and sparse convolution. Though expressive, they suffer from either the intensive computation of sampling and grouping or the limited representation capacity due to some manifold dilation. More importantly, this specially designed operation generally cannot be implemented with well-optimized deep learning tools such as PyTorch or TensorFlow, and require writing customized CUDA codes, which greatly limits their deployment in real-world application. There is another solution: transform on sparse point clouds. Given the processing relationship, transformer is naturally suitable to sparse data, but how to apply a standard transformer on point cloud is non-trivial. Global attention cannot be applied to process the large-scale point cloud like V-Mobile dataset usually has 60,000 voxels after being visualized. As for vegetation, due to the sparsity of point clouds, the number of non-empty voxels in each local window varies significantly, which cannot be computed in a fully parallel manner. As shown in this image, the blue one and the red one. To solve the above problem, we propose dynamic sparse window attention, a window-based attention strategy for handling sparse 3D voxels in parallel. Based on the above key design, we introduce an efficient yet deployment-friendly transformer 3D backbone without customers' CUDA operation. It can be easily accelerated by NVIDIA TensorRT to achieve real-time reference speed. Our approach outperformed a previous state-of-the-art method on the large-scale V-movement dataset with remarkable gains. We can see the figure here. The red is our method, and the previous data such as PVRCN++. Next, I will give some details of our method. I mainly focus on the most important designing dynamic sparse window attention is the core idea of our paper. For sparse data, you always need something dynamic. If you fix local windows, this voxel number will be dynamic. If you fix the number of voxel, you need the dynamic local region. Is there a way to balance these two things? The dynamic side is being proposed. We reformulate the sparse window tension into a series of tension in the local set. This set have following characteristics. First, the set boundary is bounded by window. And that means our sets are inside our corresponding window for a better learning of local patterns. Secondly, it's not overlapped. Here is for the convenience of updating feature. Finally, size equivalent, where all sets contain the same number of voxels and those are insufficient will be padded. This is for convenience of parallel computing. The course of sparse here is transferred to the number of dynamic set. Dynamic means that set number dynamically varies with the sparsity of the window. The denser window will be assigned more local sets for processing, and the sparser windows will be assigned fewer sets and less computing resource. This decouples sparsity from parallel computation as shown in the figure. This is a subset of 12 voxels. There are 48 voxels in this window, and 4 sets will be assigned for processing. DSVT is a backbone for processing point cloud, so it should have strong modeling power. The interaction between voxels should be considered. If only perform attention in this non-overlap set, the voxel between set and window will never interact. So we design a strategy for feature propagation in the window of the rotated set. First of all, our dynamic set partition is highly dependent on the ID of the voxel in the window. We can control the local region of each set by controlling the voxel ID, such as some sorting rules. As shown in the figure, we set two attention layers in a transformer block. These two attention layers adopt different partition strategy. One is based on the main sequence of the x-axis, and the other is based on the main sequence of the y-axis. As shown in the figure, the two types of segmentation will overlap, and the voxel of different sets will use their method interact and break the boundary of the local set. This is the performance of our DSVT. Our model can be easily deployed by the technology to achieve real-time speed, and the performance is significantly better than the previous best model. We propose DSVT, a deployment-friendly yet powerful transformer-only 3D backbone for 3D object detection, which can be accelerated by NVIDIA technology with real-time running speed. We hope that our DSVT cannot only be a reliable point cloud processor for 3D object detection in real-world application, but also provide a potential solution for efficiently handling large-scale sparse data in other tasks. Okay, that's all.